So the first two problems involve this notion of continuity. Um, so the idea for the first problem with continuity is that, mm, yeah. So if one property about continuity is if your function is continuous, then the limit as x approaches whatever number f of x is going to be the same thing as you directly plugging in. That's one of the properties of being continuous. Okay, so I got a question about when will the homework be graded. So the homework was due yesterday. I would expect it to be finished grading after a week. So you should get your grades back by next, what was it, Monday? Next Monday. All right. So this is one of the properties of being continuous. And so hopefully you remember the definition of being continuous. Maybe I should write it down. Or maybe I can find it from the slides and paste it in. That would be a bit faster, wouldn't it? So let me pull this up on a separate window here. So to be continuous means that you have that the left and right limits are equal to one another, and that the well, okay, actually, I guess I should unpack this. So in the slides, you get the following. I don't want to put that there. I want to put that. I guess I can't put pages on top of each other. I'll put it off to the side here if it'll allow me to. Right. So you get this by definition. This equation, which is actually what I just wrote. But when you stare at this limit, you realize this is a two-sided limit, which means that you must have that the two sides agree with each other. So, and this is sort of unpacking what it is. So to be able to say f of a, you must have that f of a is a quantity that exists. And so when you unpack this statement, it's actually saying three different things. This side exists, and the two sides are equal. For the first problem, what we're doing is we're going to end up using this last equality. So the first thing to note is that this function is a continuous function. Cosine is a continuous function. This polynomial on the bottom is continuous, and division of continuous functions is also going to be a continuous function. So I guess to be explicit, we would say that since cosine of theta over theta to the fourth plus 1 is a continuous function, then you have that this limit is going to equal cosine of pi over pi to the 4 plus 1. We're allowed to just plug in by definition of continuity. And now you just have to remember what is cosine of pi. It's going to be minus 1 over pi to the 4 plus 1. And so this is what you get. Okay. And part B is the same exact thing. Arctangent is a continuous function. This is continuous, so you can repeat the same argument. Since I'm going to abbreviate arctan as atan. Whoops. Parentheses t to plus 1 to the 4. That looks not like a t. Then this limit is going to be just take arctangent of 1 times 1 plus 1 to the 4th. And so who can tell me what arctangent is? Or arctangent of 1, I mean. Like, who can evaluate this? Or, like, reason through it? Nobody? Okay. So, yeah, little side calculation. So what does it mean for arctangent to, well, how do we interpret what this actually means? So arctangent is an inverse function of tangent. So this is really saying tangent of what angle is going to give you the value 1. So you have to then recall the unit circle, the various tables. When does tangent take the value of 1? And there's a slight nuance here because whenever we deal with an arc trig function, we actually split the domain. So normally, like, there's a whole infinite family of answers for this question here, tangent of what angle equals 1. But when we make it into an inverse function with arctan, we actually specifically chop a part of the real line so to make this a function instead of a multi-valued function. So the answer that you hopefully get to is that the question mark should be pi over 4, and so arctan of 1 is going to be pi over 4. Okay. And then what is 2 to the 4th power? Well, that's just going to be 8, and so you end up with, no, not 8, sorry, 16. And so then you end up with 4 pi. Okay. So hopefully this trig kind of stuff made sense. If not, then it's a good idea to find a problem set, find a textbook, find a problem set, and just practice a few problems. You can always check that you've calculated things correctly by using a calculator like Wolfram Alpha, but primarily you should be using that just to double check that your reasoning was correct. Okay. Number 2, now we still are dealing with continuity, but here we have this piecewise function. We want to find, is it, where is it continuous, where is it discontinuous, continuous left, or continuous from the right? If it is continuous, right? So yeah, because what can happen is that the function be discontinuous at a point, but it can be continuous with respect to one of the directions. Actually, why is this, this is not going to show up in the recording if I don't put my face right here, is it? I have no idea. I don't know if it's going to show up in the recording. Normally I can make my face bigger also. Oh, that's fine. Right. So first of all, we would see that each of these individual functions are continuous. So the only part where this function q could be discontinuous is at where the chopping happens for this piecewise function. So what we really want to check, or the only thing that we need to check, is what happens at 0. So we want to think about the limit of q, both from the left side and from the right side. And then we will want to compare it against what q is, what value q takes at 0, which in this case is 3. So notice how I'm going to split this apart. So if we take the limit from the positive side, that's going to be where x is greater than 0. So this this limit is going to ignore the other branches of q, and it's only going to have this cosine of x plus 8 branch. And let's go ahead and compute that now. So we can then plug in order to evaluate this, since this is now a continuous function. Cosine of 0 is going to be 1 plus 8. We get 3. Okay, compared with the other one, oops, x goes to 0 from the left, we've got the exponential function. Okay, I can then plug in e to the 0, which is equal to 1. And you can see that this 3 matches with that 3. So this would let us conclude that the q of x is continuous I'm going to abbreviate, from the right at x is equal to 0. And because this is not a 3, we know that there is a jump discontinuity. So we can answer the first question of where is q continuous. So then we can also say, maybe I'll use a different color for that. So for the question, Q is continuous everywhere except x equals 0. You could phrase that as like minus infinity to 0, union 0 to infinity, but I will just write it like this. It's a bit shorter. Does this answer make sense to everybody? Any questions? No? Okay, well, let's keep going. So then another thing you learn about is the squeeze theorem. To recall the squeeze theorem, let me see if I can just copy it from the slides. Where did it go? Okay, yeah. Yeah, that's pretty much what that is. Okay. Please paste. Good. Okay. So this statement is squeeze theorem. What it's saying is, suppose what we're interested in is this last guy. We're trying to calculate the limit of this function g as x goes to some number a, and we want to like say that it's some value L. Like we want to find this limit. The squeezing happens because what we do is we sort of squeeze this function g between two other functions, f and h. And the hope is that these two functions, f and h, are simple enough that we actually can figure out their limits, right? G is some complicated thing. F and h are simpler things that we can actually take the limits of. And if we know that their limits actually coincide, if they actually hit the same value, okay, and here's like a little picture to illustrate. So it's also in the slides. It would be nice to assume that you guys have like looked at the slides beforehand, but I'll try not to assume that. So in this picture, your h would be the red function, your f would be the purple function, and g is this complicated function that is in blue. So it's asserting that we can, if we can find two functions that bound the complicated function in blue, and that they both hit the same value wherever we're trying to take the limit at, then we can figure out what g is just because it's squeezed into a single number by the two functions on either sides. Okay. And so let's take a look at this function that we're given now. So this type of function is very common for these squeeze theorem type of problems, where you've got this cosine and you've got this 1 over theta, 1 over x. Because what happens is it's just like in this picture, actually. You've got this sine function that ends up oscillating faster and faster as you approach 0. Very common pattern that you see among problems. So this function is going to behave just like that, except for the fact that you've got this this theta to the 4. The theta to the 4 is actually what bounds the oscillations. So normally, this cosine of 1 over theta, it'll be bounded by +1 and -1, but then your oscillations will become infinite as you approach 0. The only redeeming factor is the fact that you've got this this little function that sort of kills off the oscillations. Okay, so what we want to do is we want to find these functions that bound it. Well, I'm going to tell you what is the key to this type of problem. Cosine and sine, both of these functions are always bounded above by 1 and bounded below by -1. Right? Just consider the graphs of the two functions. They oscillate, right? But their oscillations are always bounded by +1 and -1. And that is how you start this type of problem. So we start by saying we know that cosine of 3 over theta is bounded above by the function 1, and it's bounded below by the function -1. And then what can we do to this triple inequality. We can multiply all three sides by theta to the fourth, and that will maintain the inequality. Well, multiplying all three sides by theta to the 4 is going to give us something very much, well, very much what is in the beginning statement of the squeeze theorem. All right, so now we've got this statement. Okay, looks a lot like squeeze theorem. And, well, in order to apply squeeze theorem, we need that the two bounding functions have nice limits. And notice our limit is as theta goes to 0 in the problem. Okay, so I'm going to do this sort of as a diagram. These two arrows are going to be limits. So I'm going to take the limit as theta goes to 0. I'm going to also take the limit of this function as theta goes to 0. Well, what does theta to the fourth go to when I let theta go to 0? It's just going to be 0. And what about this guy? Negative theta to the 4, take the limit as theta goes to 0. That's also going to be 0. Okay. And this function in this top row, we're saying that this function is always sandwiched between these two things. So if I take the limit of this function as theta goes to 0, what does this have to be? It has to be 0 because of the bottom row. Okay, so that argument right there is pretty much squeeze theorem. You might want to write that in words rather than as a picture. I don't know if I've ever seen anyone else do this kind of picture, but yeah, okay, so to see, like, it's definitely in Craig's slides. So Craig has a slide where he sort of writes this out in words, how you would normally do it. Basically, you would write this computation on one line, you would write this computation on another line, and then you say, by squeeze theorem, this middle guy has to also go to 0. So I'm just gonna say, like, okay, yeah, this is equal to 0. Okay. So hopefully we're good on that. Okay, there's another half, right? So this time we're told these two bounding functions, and we're not told what W is at all. Yeah, well, we can do the same setup, actually. So maybe for this one, I'll try to do this in words. So limit as x goes to 5 of this lower function. Well, I can plug in, I'll get 25. I'll get 50 minus 25, which is 25. And if I take the other limit, x squared, or if I limit the other bounding function, we also get 25. And so then by squeeze theorem, we want to explicitly say this limit of the function w of x is going to equal 25. Okay. So any questions so far?
What would happen if the two endpoints aren't the same number?
Then you can't conclude that much. It's a good point. So yeah, if these two limits didn't give you the same value, the only thing you could conclude is that the function in between would have a value that lies between those two. Like you wouldn't be able to specify what specific number it is. Squeeze theorem would essentially fail. Yeah. Yeah, so in that case, like, you would maybe try to find a different technique to take the limit if you're really pressed to take the limit of this function. It's a very strange condition. Usually we don't give you such things. Okay. Right. So the next problem involves these two things that are, I wish they were on. Yeah, he doesn't lay it out the way I would prefer. Okay, so there's these things called trig limits. They're special little limits that you need to kind of memorize. They're also on the slides, but he separates them between two different slides to, like, illustrate them visually. So, but the trig limits are the limit as x goes to 0 of sine of x over x, and the limit as x goes to 0 of 1 minus cosine of x over x. And oh, he actually flips this around the other way. Okay, so in his slides he says cosine of x minus 1, but hopefully you can see that, like, if I swap these two, I just am introducing a minus 1 to the limit, and that makes no difference because this limit is actually equal to 0. So you're supposed to have these two limits memorized, is what I'm trying to say, and they help because these two problems involve them directly. All right. So we need to calculate these limits using the special trig limits and also limit laws. Great. So hopefully you can see there's a cosine of theta and a theta inside here. So that really matches with that. The first thing I would do is I would pull out the 2/5, which I can do because that is a limit law. We can just pull out scaling numbers. So we then have theta over sine theta. Now there's some, you would like to be able to conclude right away that this limit is equal to 1. And you certainly can. It's just that there's kind of a step before that. So the step before that is to actually take the reciprocal. So, and then to use another limit property. So you should know that this expression, let me maybe use a color. This expression and this expression are equal to one another, because this fraction and this fraction reciprocated are the same exact thing, right? And so there's another property of limits where you can push it into an exponential. When you're exponentiating, you can push it into the base. Like so. And then this is where it sort of makes a bit of a difference, because if this limit wasn't 1, you would have to reciprocate whatever the value is. Here we just nicely get the fact that it is 1, and so we get 2/5 times 1, which is 2 over 5. Okay, so now part B. Let's just take a look. Well, we've got this 1 minus cosine theta over theta. That matches with one of the trig limits that we that we know about. So we can split this limit into two limits by one of the limit laws. It's a limit of products equals product of limits, I guess. You could phrase it as such. Okay, so you get that. And this is equal to 0, and you should also check that this is equal to some number. So that is a technical concern. Well, the fact that you take this limit and you get that it's equal to 0 doesn't actually let you immediately conclude that the limit is equal to 0, because I'm going to preempt a little bit. You'll learn maybe a month from now, you'll learn about a quantity called 0 times infinity. Oh, come on. It's a very important type of quantity. It's called an indeterminate form. Maybe I'll also write the word indeterminate form. Which essentially means that the quantity itself actually depends on context. It depends on what kind of 0 we're talking about and what kind of infinity we're talking about. And let me also write a couple other really common ones that you'll eventually see. There's like, I think 0 to the infinity might be 1. No, it's like 1 to the infinity. There's 3 other ones that are kind of weird and harder to remember. Yeah, but what happens with these expressions is when you see the expression, you have to pause and realize that you need to work a little bit harder in order to calculate what the value actually is something we will cover a bit later in the section of like L'Hopital's rule. But that's much later, a month or a month and a half from now. But when you see what I'm trying to say is when you see the 0, you actually can't just immediately conclude that this quantity ends up equaling 0. You actually do need to also compute this guy, all because of this special little indeterminate form. You have to make sure that you're avoiding this guy. But yeah, no, this is 7, not infinity. So here we have 0. I overcomplicated things, but that's fine. Okay. And then I think maybe it'll just make sense to do this whole page, and then we can call it afterwards. Because the next stuff is like limit definition of derivative. Okay, yeah, limit definition of derivative. Right. Okay, so we'll talk about IVT. IVT. Let me see if I can copy anything from the slides. Oh, the slides don't do it in order, I think. Or do they? Wait. Derivative problems. Do the slides not cover IVT? That's really strange. I'm not. Oh, wait, there it is. Ah, goodness. Okay. So for this, I'm gonna want to copy the entire slide down. Okay. Sorry about that. Right. Well, at least me pausing lets you guys think. That's okay. So this is the mathematically precise statement about IVT. So firstly, it's very important that we have a continuous function. If you don't have a continuous function, IVT does not apply, period. You move on. The problem won't work that way. But for our problems, we do give you continuous functions. It's just you need to, first of all, check that they are continuous, and that will let you use IVT. So specifically continuous on a closed interval, and these two values are not the same. So pictorially, what this is saying is you got A over here, B over there, and you're just trying to say that the two values, like 5 is not equal to 1, is what it's saying in this picture. So we have that 5 is not equal to 1. Okay. Let M be some number between any of these two, between 1 and 5. M be some special magic number that you want to use. And IVT is then going to be able to conclude there's got to be some point along this function then where the function will spit back out that number. So maybe to illustrate this on top of here, if I can actually draw on top of this. So say that you wanted M to be this value, right? Because you're basically allowed to choose any number from 1 to 5. Choose any number from 1 to 5. IVT, as long as the function satisfies IVT, meaning that it's continuous, right? We need it to be continuous for this to hold. Then we can guarantee that there is some input that we can give to the function. Normally what we do is we draw across, we draw down like this. Oops. Make it look more straight. So this ends up being the special value that we can plug into the function. So this is saying that, like, yeah, we are able to find such a point P that when we plug into the function at P, we'll get back the value M that we were looking for. And he's just using C's and D's for some reason. But yeah. Okay, so hopefully you have some intuition behind what the intermediate value theorem is saying. Right? It's all because like there's no sudden jumps in this function. It's because it's smoothly changing from 5 to 1 that we can expect that at every value in between 5 and 1, there is going to be some time where the function takes on that value. Okay, now let's go ahead and try to use this. So we've got this function, and we want to show it has a root. Now, a root is just a place where the function equals 0. So I'm going to rephrase this by saying let f of x, we're going to call this expression the function f of x. Makes everyone comfortable if we do that. X. Okay. And we want to show that there is some f of p that is going to have the value 0. Right? Having a root means that we found some place where the function takes the value 0. Maybe I'll say for some p. Actually, I should be more specific. Yeah, because it actually tells us where we want the p to be. We want it to be between 0 and pi over 2. In 0 to pi over 2. So I'm using a little math notation here. This, just in case anyone hasn't seen this, there's a thing that looks like this, and this is called in mathematics, or element of. It can be interpreted in 2 different ways, but they mean the same thing. So yeah, I don't know why they just decide not to teach you these math shortcuts. It's very helpful. Every math major needs to learn them. Okay. So right, how do we use IVT, or how do we check that IVT will work? Well, what would be really nice, and usually we structure our problems in this way, what would be really nice is if we plug in these 2 n values and they work out as being the 2 n values in our picture. Let me use my cursor. So it'd be nice if like pi over 2 acted like this guy, 5, and that the 0 would act like this 1 here. So what we will do is we'll just do a quick test. We'll test f on the endpoints. And what are we hoping for? We're hoping that one of them is a positive number and one of them is a negative number. Because if one of them is positive, the other is negative, we know that the interval on the y-axis is going to then contain 0. 0 will be somewhere in between. And then IVT is going to say, oh, then there has to be some exactly this statement. There has to be some point in this interval such that the function will equal 0 on that interval, or on that point. Okay, so now we're just going to test. So let's see, cosine of 0 is equal to 1. Maybe I'll just like specify it all out. Okay, so cosine of 0 is going to be 1, so we got 2 minus, and then sine of 0 is 0, so we get the value 2. Okay, that's nice. And I wish I had a bit more space. And 2 times cosine of pi over 2 minus sine of pi over 2. So that's if we just plug in. And what do we get in this case? So cosine of pi over 2, let me think, is going to be 0. Minus sine of pi over 2 is going to be 1. So we get 0 minus 1, which is negative 1. And I'm doing the calculation mentally. Hopefully you can also do the calculation in a reasonable time. And so notice we have one evaluation give you a positive, the other one give you a negative. So looking exactly at this statement here, let m be any number strictly between f of a and f of b. Well, we found f of a is one of these guys, 2 maybe, and then f of b is this negative 1. Okay, 0 is a number between 2 and negative 1. So how do we want to phrase this? So I'll say I'll do a different color, and I'll copy what I wrote before. Since f of x is continuous, IVT applies. And since 0 is in the interval from -1 to 2, IVT guarantees there is some p inside of the interval 0 to pi over 2 such that f of p equals 0. And you can sort of also say, like, so p is the root as the very last little statement. It sounds very precise, and that's, well, that's how math is supposed to be. But like, if you actually understand what is being said here, you might be able to simplify just a little bit. But yeah, if you write that down, that'll be good. But you only know this because of, like, say, this work here. So you need at least this part and this part. This was just a bit of setup to explain to you guys what we're trying to do. 6 is also going to be very similar. But now that I've at least shown you how it works the first time around, we can maybe go through this one faster. So we want to show, using IVT, that there is, well, okay, that this equation, f of x is equal to g of x, where f and g are given above, that this equation has a solution in this interval, okay? And it's also saying that, like, this having a solution is the same thing as saying that this difference has a root, okay? So the thing that I would do is I would just call this guy another function name. So I'm going to say let h of x be equal to the difference, and then I'm going to write down what that difference actually ends up being. So this is 5x squared minus e to the x. Okay. So this is the function that we're actually dealing with, and we want to show that it has a root. So I want to show that h of p equals 0 for some p in the interval from 0 to 1. Okay. And we can do the same strategies before. We hope that these endpoints will actually do the trick. I should also say, like, what happens if that doesn't occur. So if those endpoints don't work, usually what you do is you then try to like squeeze in on it, try to find like someplace where the endpoints will give you the right value. Usually it's because the function isn't just going down or going up, but like it has like some bend to it, and then you basically want to find like the minimum. You want to find a maximum, and then you use those to anchor your or to figure out like where your interval should be that you test for. But we give you easier problems than that. Okay. So anyway, what am I doing? Okay, I'm plugging in. So I'm plugging in h of 0. I'm plugging in h of 1. And let's see, h of 0, we're going to have 0 minus e to the 0, which is going to be minus 1. H of 1, we're going to have 5 minus e. Well, just e. I don't need to say e to the 1. Okay. And then the crucial thing is to notice this 5 minus e. I would hope that everyone knows, but perhaps everyone doesn't. What is a decimal approximation of e? E is approximately 2.718. Okay. Just like how you kind of know pi is 3.1415, you should kind of remember e is 2.718-ish. Add on an infinite stream of decimal values afterwards. But what's important here is that this 5 minus e is a positive number. Okay, so h of 1 gave you a positive, h of 0 gives you a negative, and what we're trying to do, we're trying to find some place, or we're trying to guarantee that 0 is going to be in this interval, and it is because, well, it's exactly the same as above. So the statement we would want to write is that, do I have enough space here? Maybe I need to write it here. Yeah, so h of x is continuous, so can apply IVT. Which says there is some p in the interval. Yeah, interval 0 to 1. I was just reading my handwriting. My handwriting got a little bit weird. Such that, okay, so I just use an abbreviation. Just s dot t dot normally is how people write it. Because we in math say such that all the time, and it gets kind of tiresome to write it in full. So st is such that h of p is equal to 0. So and this 0 is coming about because 0 is in between the two outputs of this evaluation of h. Right? This is some positive number. I didn't specify what the positive number is, but because we are bounded between. So maybe if you really wanted to be extra careful, you might want to say that 0. I'm writing things out of order. 0 is inside of the interval -1, comma 5 minus e. Okay, this is the output window, the window in the y-axis, f of a and f of b in the statement of IVT. And we know 0 is in between this, so then IVT says that there is some p such that the function evaluated at p will give you this value 0. Okay, so I'm just unpacking that little shortcut, the little statement I sort of hid in here. And then the last thing is we kind of want to relate this back to what the problem is actually asking for. It actually wants us to find a solution for the equation f of x equals g of x. So I will just relate this back by using some implications. So this fat arrow means applies. So first of all, well, what is f or h? Sorry, what is h? H, we define h to be f, the function f minus the function g. So now I'm just unpacking that. And then, well, we can move this function to the other side, or this evaluation, this number to the other side. And then I can explicitly say this p is dependent, well, for p, for some p, I should say some p, not just for p, but trying to be a bit precise. For some p in the interval 0 to 1. So if you're confused, that's completely understandable. This is very mathematically rigorous, and it's really like your first taste of how it feels to write some kind of a proof, a mathematical proof. It feels very technical. It's like all these little logical nuances, and you kind of have to get used to it. It takes a bit of time to get used to it, to get your brain sort of accustomed to this strange logical way of thinking. So yeah, don't feel bad if it takes you like a few hours to like stare at it to make sense of like what exactly is IVT saying and unwrapping all this stuff. Okay. We have 2 minutes. I think we should still do 7 because it's very related. So let's do 7. We might go a little bit over time, but then we'll end it afterwards, unless there are questions, of course. Right. So we've got a car reading 60 miles per hour at 170. Okay. So what I'm gonna do, or what I did here, is I listed the data as a bit of a table just so that it looked nicer to me. So we've got time and we've got velocity, and I'm sort of hinting velocity as a function of time. This is really what the problem is about. We want to think of velocity as a function of time. And in order to use IVT, well, we need continuity of some function, right? So the function in question is going to be this velocity function. We want to assert like that the velocity function is continuous at some point, and then we can use IVT. Okay, so what does this say? Using math, argue why the speedometer must have read 65 miles per hour at some point between 1 p.m. and 2 p.m. Okay. Well, actually, we can just apply IVT. uh, so like, since velocity is a continuous function, at least you would hope, right? I can't spell function. IVT applies. And since 65 is a number between these two endpoints on the y-axis, IVT guarantees that there is there's some time t in this interval from 1 to 2 such that I can spell this out, such that v of t, what was that? V of t is equal to 65, which is exactly the statement that it's asking you to assert. So like this statement is this statement exactly. Okay. So that is number 7. Are there any questions? Anything you want me to go over last or we can end here because we're technically at time. No? Okay. Then I'm gonna stop the recording. And